Now let's consider what happens to lengths perpendicular to the direction of relative motion. So let's suppose that we have a rod on a train, okay, which in the frame S prime has a length of let's say 1 meter, and a rod S, which according to the ground observer also has a length of 1 meter. So they could have compared these lengths with each other when S prime was at rest, but now S prime is moving with respect to S at a speed v, let's say along the x direction. And the rods are held perpendicular to the x direction, so they're held, let's say, along the y direction. So this rod is at coordinates y1 and y2, and this rod is at coordinates y1 prime and y2 prime as measured by observer S prime. So the length of this rod, according to observer S prime, would be given by a simultaneous measurement of its y coordinates, and you subtract the difference between them, and that should result in the length of the rod as measured by the moving observer. And similarly, the length of the rod as measured by the ground observer should be y2 minus y1, which is the length of the rod as seen by the ground observer. Now, our special relativity dictionary tells us that nothing special should happen in the direction perpendicular to the direction of motion. So y2 prime should be y2, y1 prime should be y1. And this just came about from the principle of isotropy. There's no preferred direction except the x direction, so it's not clear that anything should happen in the perpendicular direction. And so therefore this dictionary tells us that the lengths of the rods will be measured to be the same. Now what that means is that rods placed perpendicular to the direction of relative motion appear to be of the same length. That is, the observers in frame S will also see that the rods which are moving along with the train appear to have the same length L. However, we saw that this is not true if the rod were placed along the direction of motion. If they're placed along the direction of motion, the rod which is moving along the train would appear to be length contracted. Now let's try to understand the same effect from the principles of special relativity. So let's suppose that we have an observer S in a frame S, and they have a rod of length L with them. And let's suppose that there's a moving observer on the train with a rod of length L, according to them in their rest frame, moving with a speed v towards S. And let's suppose that that at the instant that they pass each other, okay, we've arranged for it so that this end of the rod, these ends of the rod just pass each other. What we want to know is, do the tops of the rods also appear to pass each other at that same instant? Now let's suppose we do an experiment by imagining that this rod S prime has a piece of chalk on it, and the rod S has a piece of chalk on it. Okay, and as they pass each other, if the rods, as they pass each other, if the rods or the tops of the rods touch the other rod, they will leave a mark. So now as S prime passes S, if S prime is at least as long as S, a little bit of this white chalk will be left on the rod of observer S prime. And similarly, as S prime passes S, if the rod on the train leaves a little bit of a mark, would leave a little bit of a yellow mark on the static rod, or on the rod in the frame of S, if the rod S prime appears to be shorter, or at least as long as the length of the rod L as seen in frame S. Okay. So now let's suppose that, let's just suppose, for example, that it's possible that the rod's length S prime, as seen by the ground observer, is longer than L, or is shorter than L. So let's suppose this rod appears to the ground observer to have a length which is shorter than L. Then what would happen is that as they pass each other, the rod from the train would leave a mark on the rod in the frame S, but the rod on the platform would not leave a mark on the rod in the train. Okay, and the events of the rods passing each other are simultaneous as measured by both the ground observer as well as the train observer. Remember that simultaneity is only relative at a distance along the direction of relative motion. Perpendicular to the direction of relative motion, these events are simultaneous as seen by both observers. That is, all points on the rod appear to pass each other simultaneously. Okay, so now if this were true, that the rod appeared to be shorter as seen by observer S, then observer S will see a chalk mark on their rod, but the moving train observer will not get a white mark on their rod. So according to them, they would have seen that observer S's rod, they would conclude that observer S's rod appears longer to them. Otherwise it would have left a mark on their rod. And so now we conclude that there would be a way to tell who is in relative motion to whom. Okay, in other words, S would appear to be a preferred frame relative to frame S prime. Okay, or vice versa, because in one of the frames there is no mark left on the rod, but in the other frame there is a mark left on the rod. However, the situation between S and S prime is perfectly reciprocal. They both have rods of length L. In frame S, the frame S prime appears to be moving to the right at a speed v. In frame S prime, the rod appears to be moving to the left at the rod of S appears to be moving to the left at a speed v. Okay, so therefore we would run into a contradiction if we assumed that one of the rods appears to be smaller to one observer, because that would mean that this reciprocity is broken and we can pick out a preferred rest frame. Since that is not the case, we must conclude that rods placed perpendicular to the direction of relative motion do not exhibit any kind of length contraction.